A lot of the work we've been doing in statistics so far has been based on the normal distribution and what we refer to as the Z distribution. So the Z factor in our multipliers. When you do your preliminary confidence intervals in most statistical chapters on sampling, you start with a Z formula for calculating your confidence intervals based on a normal distribution. As your sample size varies, though, the Z distribution, the standard normal curve, is not an accurate representation of what's going on in the process as you go through. So what we want to do is look at the T distribution, which the chapter moves into, because in the future we're going to base most, if not all, of our confidence intervals on a T distribution rather than a Z. What you're going to see is that the Z distribution is the limit of the T distribution as our degrees of freedom increases toward infinity. So for large sample sizes, there's not going to be a big difference. That's what we want to take a look at now. So I've got a set of percentage data here for flu shot data going on that I might want to analyze. So it's a very large sample. I've got over 10,000 data points here in this distribution. So I want to know what its mean is with some degree of accuracy, maybe a 95% confidence interval. So typically if I want to calculate that myself using different parameters of Excel, these are the different values that I want to come up with. And for the sake of discussion, I want to calculate a confidence interval based on Z and a confidence interval based on the new T factor that we're learning about, and see what's different about the two as I go through. So if I bring my data into this distribution, I've used standard Excel functions for this. You can see up here at the top. My mean is roughly 69.8, and my sample size was 10,040. So I can calculate my standard deviation as 20, my standard error as roughly 0.2. And in this case, I'm looking for a 95% confidence. So I'm going with an alpha of 0.05 for 5% error. It's a two-tailed distribution, both with the T and the Z, so I want to get my alpha 2, so I know how much should be under each of my factors. So this is kind of my parameter setup, if you will, as I go through. Always start by just getting your basic parameters that you'll know you'll need in the formula. Then I can take my Z distribution. I can go out and get my Z factor using my norms inverse function off of that 0.025 to get my norms of 1.95. I can multiply that by the standard error that I pre-calculated because that's needed in the formula, and that becomes the interval factor for knowing my interval. So my confidence interval is going to be the mean value 69.8 plus and minus that 0.39. So I can do that calculation here. Here's the upper limit using the plus and the lower limit using the minus. So if the data is reasonably normal, I can say not just that my mean point estimate is 69.8, but that I'm 95% confident that my mu will fall between 69.4 and 70.1. Notice the difference there. The mean estimate is based on X bar, the actual average of the sample. Using it as a point estimate to come up with a confidence interval, I'm not coming up with a confidence interval for this sample. I don't need it. I know what the sample is. But I want to know about the population from which the sample was drawn. So the mu of that population, I'm 95% confident will be between 69.4 and 70.1. Now I can also do that calculation based on the T curve, the T distribution. For that I need a degree of freedom. In this case it's n minus 1. So for my sample size of 10,040, I subtract 1 and I got my degree of freedom of 1039. My T factor for that requires that I know the alpha of 0.05 as well as that degree of freedom. Notice I didn't take here the T inverse function of the alpha 0.5. Really it's the 0.025 that I want if I'm writing it out, alpha over 2. It's just a quirk of Excel. Always check Excel and how it does a T distribution. The T inverse function and the T dist function in my version of Excel enters the alpha and does its own internal alpha over 2. So you need to look at the help screens of the documentation for your Excel to make sure you're using the function correctly. Because right here it looks like I'm doing it wrong, but that's only because Excel wants alpha, not alpha over 2. In some other statistical tools, it might be looking for alpha over 2. So be careful how you do that entry as you go through. Okay. But my T for a two-tailed 0.025 distribution is a 1.96 under the T distribution. Notice that's a little bit bigger than the Z value was under the Z curve. So my distribution is going to be a little bit wider under my T distribution because the T allows for that increased accuracy as I go through. If I multiply the T factor by my standard error, which I need for the formula, I now then know that under the T distribution, my confidence interval is going to be the 69.8 mean plus or minus 0.391. So that gives me a confidence interval from 69.4 to 70.1. And I've got a formula here that simply takes the width of that going on, looks at the difference. So the difference between the z curve and the t curve is very, very small. I've got 4 zeros in those significant decimal places. So for the most part, when I'm dealing with a sample size of 10,040, whether I use the z curve or the t curve doesn't really make any difference to most practical purposes. If you're dealing with something that's really down in the nitty-gritty details where you need high precision, note the difference. Generally, because you can plug these numbers into Excel in a matter of seconds, you might as well use the t interval, which is more accurate than the z interval. Back when I took statistics 20, 30 years ago, you had to look these numbers up in tables, and the t tables were huge compared to the z tables because of all the different degrees of freedom. It was simply easier to do the z curve calculation when you were using pencil and paper. But today in calculators and in Excel, it doesn't really make any difference. So my recommendation is to always use the t interval. If you know the sample size for the degree of freedom, you'll get a more accurate response as you go through. That for large sample sizes, the z and the t interval is virtually the same to such a small degree of freedom. But let's, so if instead of calculating all these numbers myself, I'd gone out and run the Excel descriptive statistics, I would have gotten to the same place very, very quickly. You don't have to do these calculations by hand. So if you do descriptive statistics, you might or might not at this point in the class have been adding that 95% confidence interval. Notice that the Excel number gives me my 0.391. The number that Excel gives you is this two-tail t distribution for your confidence. So when you ask for a confidence interval from Excel, it's always giving you the t interval, not the z interval. You'd have to read some documentation in Excel to know that, or just compare the numbers that you do to calculate yourself. So the Excel spreadsheet formulation of the descriptive statistics will always give you the more accurate t distribution as you go through. But for large sample sizes like this, the difference between the two is negligible. Let's look at a smaller sample, a sample with a sample size under 30. Very similar data, but I'm going to go through the same process. So I want to calculate the exact same properties as I go through. On the small sample, I got a 68.3. I'm still looking at my alpha over 2 of 2.5%. My z formulation is the same, so I'm still looking for my 95%. But my confidence intervals end up being different. So here in the z curve, I can say with 95% confidence that my mu will fall between 63.5 and 73.0. When I do the same calculation for my t, I get a very different interval. I get 63.3 to 73.2. So here the t curve is a full, almost 0.42 wider than the z curve, and that can make a big difference because these confidence intervals are not the same. Suppose the real mu is 63.4. Well, according to the z, that would be outside the characteristic limits that I want, but the t predicts that it might be. So if I use the z distribution to calculate this confidence interval, I might make some very bad mistakes going forward because I'm just as likely to get a number of 63.4 as I am to get a number of 63.6. The confidence interval of the mean simply says I have a 95% confidence it will fall somewhere in the interval, not that it will go near the mean. The numbers near the edges are no less likely than the number in the middle. I'm simply saying that I believe the value will fall in this interval. Again, if you do the descriptive statistics in Excel, you end up with a variation of the t times SE is based on the t distribution. So the moral of the story is for small samples like this one, 29 data points, make sure you're using the t distribution to come up with your confidence interval. For large distributions, you have the choice doing it one way or the other. You get virtually the same answer. But when other things being equal, if you know the sample size, which is the only additional piece of information you need to do the t interval, go ahead and do the t interval rather than the z. The only time you would use the z is if you're given data about the sample without actually being given its values, so you don't know how many data points there were, you would have to use the z distribution. But even when they don't give you the values, they usually tell you how large the sample was. So when in doubt, use the t interval distribution. You'll get a much more accurate answer.